Hello everyone, welcome to our webinar today. I'd like to introduce Professor Mika Kortesniemi. He will be the moderator of today's session. Mika, the stage is yours.
Thank you, John, and welcome all to the second day of the International Medical Physics Week of the IOMP. As John said, my name is Mika Kortesniemi. I am Chief Medical Physicist and Adjunct Professor in Helsinki University Hospital in Finland, and I am happy to moderate this event. Today we will have 1 hour webinar, which is entitled Artificial Intelligence and Medical Physics, the initial experience of the SINFONIA Horizon project. As we can see, the artificial intelligence is developing with exponential speed in many fields of science and life, also in medical physics, in our practical field of work. And it's important to recognize how this very strong and fast development affects our profession, the methods we are using in our everyday work, and of course, our research. And today we are talking about artificial intelligence and SINFONIA. The SINFONIA is a 4-year research project developing tools for comprehensive risk appraisal for detrimental effects of radiation exposure during the management of patients with lymphoma and brain tumors. And it's really extensive project with 14 consortium partners from 8 different countries. In this webinar, we are happy to have 2 prestigious speakers and experts on this field. I will introduce our second speaker after the first talk. And we will have discussion at the end of this webinar, meaning after the second talk. And I would encourage you all to use the chat to write questions and comments during the talks. And I will try to collect the questions to the end. Our first speaker is Professor John Damilakis from the University of Crete. He is also the scientific coordinator of SINFONIA project. And John will present an introduction to artificial intelligence and explain CT, the computed tomography, organ dose prediction using neural networks, which is a part of AI in deep learning. And now we will go to the first talk. Please, John.
Thank you, Mika, for your kind introduction. So what's the relationship between archaeology, computed tomography, and AI? I will try to answer this question today. No, you're not in the wrong webinar. This is the IMPW series of webinars. I'm John Damilakis, and the title of my talk is AI and Medical Physics, the initial experience of the SINFONIA Horizon project. And here is a brief outline of my presentation. So first I'll begin with a brief introduction to SINFONIA project, then we will move into machine learning and neural networks, the basics. And after this introduction, I'm going to kick off a short demo to train a model to predict lung dose from computed tomography data. And then I'll share with you my initial experience from our research work on AI. And finally, I will reveal to you the relationship between archaeology, computed tomography, and AI. So let's start from the beginning. I'll briefly introduce SINFONIA project. According to Wikipedia, SINFONIA in Greek means agreement, but also concord of sound, harmony. And I do believe that SINFONIA will be a harmonious project. SINFONIA is an acronym, of course, and the full title is Radiation Risk Appraisal for Detrimental Effects from Medical Exposure during Management of Patients with Lymphoma or Brain Tumor. This slide shows the SINFONIA partners, 14 institutions from 8 countries. And our main aim is to develop novel dosimetry tools and methodologies that will be somehow demonstrated on two exams, two clinical exams, lymphoma and brain tumors. We are planning, we collect actually, we are currently collect data from patient procedures, data on exposed medical staff, carers and comforters, big data. So our methodology includes not only a lot of dosimetry and risk appraisal science, but also machine learning. So let's go to AI and machine learning now. Machine learning model development is a new, sometimes intimidating activity. So first thing first, we need to know what problem we are trying to solve and ask the right question. Albert Einstein said that the formulation of the problem is often more essential than its solution. And this is applicable to machine learning. The identification and right formulation of the problem is the key to success. As I have already mentioned, SINFONIA is about doses and risks, radiogenic risks, and machine learning aided organ dose estimation is one of the issues we are trying to address here in the University of Crete. So we have focused on patient-specific and equipment-specific Monte Carlo dosimetry. Using CT images, we create the model of the patient, and Monte Carlo simulation provides dose distributions, provides the 3D dose distribution. So it's important to know that there's voxel-to-voxel correspondence of those images with CT images. And this is important. This is shown here. So on your left-hand side, the CT images, and on the right side, the dose distributions, So there is a voxel-to-voxel correspondence, and we have data, we have images, CT images, but also dose images. And the 3D dose distribution, obviously, is an important source of information. However, we need to estimate organ doses. And we use tools to delineate radiosensitive organs and extract organ dose information. This is a time-consuming process. As you and I know, this needs time. And the question is, could machine learning assist us in this effort? The workflow for developing and implementing a machine learning model is based on the steps shown here: data acquisition, data pre-processing, feature engineering, model selection, model training and testing, model evaluation, external validation, model deployment. It's a long and difficult process. Although each of these steps is important, data acquisition and preparation deserves special attention. We must ensure high quality big data. Otherwise, you know the quote, garbage in, garbage out. For compute tomography, we usually collect data from the PACS system. DICOM files include metadata useful for the development of machine learning models. We should know, of course, how to get and use this information and how to anonymize it. This is important. There are many tools around to perform DICOM data anonymization. And for data storage, a centralized backup solution is very important. So in my department here in the University of Crete, we have developed a platform, a server, a workstation actually, with a NAS network attached storage connected to PACS to collect data in an organized way for machine learning purposes. This is very important, how to collect data properly for machine learning. And data labeling is the next step, very important step, especially for supervised training. So in our workstations, we have images, we have Monte Carlo produced 3D dose distributions, organ and tissue doses, organ volumes, and also our Excel files include relevant DICOM metadata, such as exposure parameters, scan ranges, and so on and so forth. this point, I'd like to define a few basic terms for those who are not very familiar with machine learning and artificial intelligence. So a feature is an input-independent variable. And an example is here, a training set to predict lung dose from CT. Features are the various dose predictors, tube potential, tube load, scan length, etc. And a label is the thing we are predicting. In this example, the label is the dose to the lung. Of course, sometimes we are working with DICOM images, not Excel or other type of files. And in CT imaging and in imaging in general, we annotate images with labels. Labels are predetermined and are chosen to give the model, the machine learning model, information about what is shown in the image. So in this case, the label structure is the subcutaneous fat. Now, in supervised learning, the training set includes labels. The input data file can be an Excel file, a CSV file, or DICOM images. And annotated data are used to train the algorithms to recognize findings. Machine learning has been used in detection, classification, management of findings, various tasks. The machine learning model can be used to make a prediction or recognize a structure. For example, machine learning can make a prediction of malignancy, or we can use it to segment an organ, to make organ segmentation. Now, data pre-processing and feature engineering is a huge topic because different kinds of data need different methods for pre-processing, but there are some common methods. For example, we need to deal with missing values, outliers, categorical data must be somehow converted into numerical features. Sometimes we need to normalize parameters to rescale them. Sometimes we need to remove features, add features to improve the model, and this is feature engineering. And if we simplify the model, this is dimensionality reduction. So the important point here is that data preparation is needed, and this is a very important process before any machine learning model selection. Let's go now to model selection, model training, and model validation. Data is not enough to train a computer. We also need an algorithm. And the question is, how do we choose which model to use for our task? There are several, as this slide shows, there are several categories of algorithms, and each category is divided into many algorithms. So model selection is the process of choosing the best statistical machine learning model that addresses the problem. And fortunately, we have tools to make that selection. So there are several machine learning libraries, open source machine learning frameworks like PyTorch, Keras, TensorFlow, and so on. And this is a great advantage that this software, these frameworks come with no cost. These are open source frameworks. These libraries make our life easier because we can perform complex tasks without writing many lines of code. And for training a model, we initially split the model into sections: training data, validation data, and testing data. And the basic idea is that you train the algorithm using the training data set, you tune the parameters using the validation set, and then test the performance of your model on unseen test data set. This slide shows the well-known and very, very widely used k-fold cross-validation method. You split the training set into k groups, subsets of data. In this case, k is equal to 10. So 10 subsets, and you train the model on 9 subsets, and then evaluate the model on the subset that was not used for training, and this process is repeated 10 times with a different group, different subset each time. Okay, let's go to artificial neural networks. These are widely used in AI, as we all know. A neural network is a collection of software neurons connected together, and they are capable of sending messages, these neurons sending messages to each other. So the network is asked to solve a problem which it attempts to do over and over, each time strengthening the connections that lead to success. And let's understand how this is done. Let's construct a neural network that predicts if a computed tomography examination will be above national DRLs. Neural networks are made up of layers of neurons, as I have already mentioned. These neurons are the processing units of the network. And first we have the input layer, which receives the input. The output layer predicts our final output, and in between, the hidden layers exist, which perform most of the computations. And here is the Excel file with our data. This file is fed as input to each neuron of the first layer. Neurons of one layer are connected to the neurons of the next layer through channels, and each of these channels is assigned a numerical value known as weight. The inputs are multiplied to the corresponding weights, and the sum is sent as input to the neurons in the hidden layer. Each of these neurons is associated with a numerical value called the bias, which is then added to the input sum. This value is passed through a threshold function called the activation function. And the result of the activation function determines if the particular neuron will be activated or not. So activated neurons transmit data to the neurons of the next layer over the channels. And in this manner, the data is propagated through the network. And this is called forward propagation. In the output layer, the neuron with the highest value fires and determines the output. These values are basically a probability. For example, here a neuron associated with a value above DRLs has the highest probability. That's the output predicted by the neural network. However, the network may have made a wrong prediction. How does the network figure this out? Please keep in mind that our network has yet to be trained. So the predicted output is compared against the actual output to realize the error in prediction. This information is transferred backwards through our network, and this is known as backward propagation. Based on this information, the weights are adjusted, and this cycle of forward and backward propagation is iteratively performed with multiple inputs. This process continues until the network can predict if the dose values exceed the DRLs or not correctly. And this brings our training process to an end. In terms of artificial neural networks, an epoch refers to one cycle through the full training set. So training a neural network usually takes hundreds of epochs. And model evaluation, a learning curve, is a plot of model learning performance over time. This is loss over time as a function of time, as a function of epochs. It's the same experience. And a loss function is a measure of how good a prediction model is in terms of being able to predict the expected outcome. Training should always be evaluated, and there are several metrics to evaluate your model. And this slide shows some of them. The area under the ROC curve is very popular. I'm sure you know ROC. And an ROC curve shows how well a model can classify binary outcomes. It is used mainly in classification models. The area under the curve is calculated and used as a metric showing how well a model can classify data points. So the horizontal line that travels down up here is the cutoff value. The orange dot that travels along the ROC curve corresponds to the false positive rate, the true positive rate for the cutoff value given in the plot on the right. So it's really important, especially if you are working with classification problems. It is very important to understand how the receiver operating characteristic curves, how the theory works. And after this brief introduction on machine learning, I'm going to kick off a demo now, where I'm going to train a model to predict lung dose from chest compute tomography. AI-assisted organ dose estimation is included in SINFONIA's tasks, as I have already mentioned. The set of features includes, as it is shown here, KV, MA, scan length, lung volume, WED. So these are the dose predictors, and the dependent variable is the lung dose. And okay, I think I have to stop stop sharing this screen, and I will share this screen. I hope you can see it. I need to reconnect to connect. So this is a piece of code here in a cloud-hosted Python notebook. It is connected. Let me have a look. Yes, yeah, yes, it is connected. So what I want you to focus on first, the libraries have been imported here, sklearn and keras, and our data set has been imported also here, and some kind of pre-processing code written here for scaling the variables. And we split the set into 70%. This 0.3 here is 70% training and 30% testing data. And then there are these things here. This is the neural network, actually. And you see the nodes and the activation function here. And there is this line, model.compile line. There are 3 parameters here. The loss, the optimizer, and the metrics. And what the loss function does, it measures the results over time, how well or how badly does it. And then based on that, it passes data to the other function. Here, the optimizer function, which generates the next guess. And if we keep repeating this, guesses get better and better. And the epoch, the number of epochs is here, 100, to keep it short. So it means the model is doing that cycle 100 times. So the model takes a look at the parameters, feed these parameters, take a guess, measures how good or bad it is, and repeats. Then it repeats the process, and the optimizer makes it better and better. So I will start doing that, hopefully. Murphy's, oh, okay. I have to upload my data. So good to, okay, fine. So I guess it's the Murphy's law. Let's see if everything, okay. So epoch, this is the first epoch, it works. Second epoch, and you see here the loss. It's getting better and better. Started from 94%, 13, 12, 8, and so on. So I'll stop here sharing this screen, and I'll go back to my presentation. And I think I need to, oh, sorry. So I need to share again my PowerPoint presentation. That's fine, and we'll go back later on the demo. So it will take a few minutes to train. So okay, I will get into our work here. One of our AI-assisted organ dose estimation approaches is shown here. So using clustering and thresholding, a masked image is produced. This is a kind of dimensionality reduction technique. We flatten the city images, and the feature matrix consists of features such as Hounsfield units, KV, MA, and so on. So in a sense, we convert images into millions of data points, reducing the amount of data need for training. The amount not of data, the amount of images, of exams. And this slide shows preliminary results, a head city image, and the predicted dose distribution. Doses are in milligray, in soft tissue, and bones. Very promising, very impressive, in my opinion, results. So these are, again, predicted images, are not the ground truth. This is not, these images are not from the 3D dose distributions produced using our Monte Carlo technique. And time is very limited, unfortunately. So I'll try to reduce the length of my presentation a little bit. So let's go to convolutional neural networks. Flattening the image and feeding it into a neural network is not always a good option. So that's why we use convolutional neural networks. Here the hidden layers are convolutional layers. And this is an example of convolution. So I'm just looking at one of the pixels here, the central pixel with a value of 94. So if you take a look at the neighbors, and then you get a filter, which is the blue matrix here, you multiply the value of each pixel with the corresponding value in the filter. I guess you are more or less familiar with this. So that's a convolution in the context of machine learning. And in this slide shows the convolution operation. So the filter moves to the right with a certain stride value, and then it hops down to the image with the same stride value, and so on. And to reduce data size and decrease the computational power, this is important. To reduce the computational power, we do some pooling. So we have 16 pixels, and I'm going to pick the biggest value, which is 96, and then the next four on the right, on the right-hand corner, the biggest value is 78, and so on and so forth. And then after that, we can flatten the final output and feed it to a regular neural network. Going back to our SINFONIA work, we are also currently working on AI-assisted dose estimation for partially exposed organs and organs exposed to scattered radiation. To achieve this, we add missing tissue slices using mathematical phantom. So you can see here in this animation, so we develop hybrid models, half patient, half phantom. And this is shown here how we combine slices in order to do this partial exposed organs dose estimation work. And in our armory, we have GANs. So a GAN is a generative model that is trained using two neural network models. So one is the generative network that learns to generate new plausible samples. And there is another neural network, the discriminated network, that learns to differentiate generated images from real images. So the input here is both generated and real images. And the two networks are set up in a contest, and we train the discriminator for a few epochs, then train the generator for a few epochs and repeat. And this way, both networks get better at doing their tasks. And we are using GANs in computed tomography dosimetry. The generator is used to generate synthetic dose images, and the discriminator is used to discriminate the synthetic from the ground truth. And these are preliminary results, the predicted image and the ground truth produced using our personalized dosimetry method. Again, also here, very, very promising results. And the final steps are validation and deployment. and generalizability is a problem, a general problem in AI, but we have to understand that AI is not a one-size-fits-all technology. So every project is customized to solve a particular problem. And now I will go back to the demo and see what happened here. So, okay.
John.
Yeah.
Sorry. Yeah.
Okay, 1 minute or two. Thanks, Mika, for the reminder. And so 100 epochs, and the loss is a function of epochs. Here in the beginning, as we saw, the loss was very high, and we are getting better and better results. The line here is not smooth, so tuning of hyperparameters is needed, training data, pre-processing is needed. So yeah, but it is okay. I mean, this is how to train. I just want to show you how we train models. And I will finalize my presentation by answering the question in the beginning. So what all this have to do with archaeology? Some days ago, I read in UCL's website, UCL is the University College London, that researchers have solved the measure piece of the puzzle that makes up the ancient Greek astronomical calculator known as the Antikythera mechanism, a hand-powered mechanical device that was used to predict astronomical events. And it was found in a shipwreck near Crete in a tiny island, Antikythera. And this prediction tool was, in my opinion, the first AI system in the world. This paper was published 1 month ago in Nature Scientific Reports, and the authors mentioned that the most complex piece of engineering to have survived from the ancient world is the Antikythera mechanism, 2,000-year-old device to predict the positions of the sun, moon, and the planets, as well as lunar and solar eclipses. And this is my final slide, I think. This is from the PLOS ONE publication on compute tomography reconstructions of the fragments. And some symbols here, alpha, gamma, sigma, on your right-hand side are known to you from physics and mathematics. So, okay, it's time to finish. Many thanks to all of you for your participation. I'll be happy to answer your question after Habib's presentation. Thanks.
Thank you, John, for this thorough presentation of AI issues, and it was really nice to see the demonstration, practical demonstration running on. So thank you. I will take questions after the second talk. And now our second speaker is Professor Habib Zaidi. He is Chief Physicist and Head of the PET Instrumentation and Neuroimaging Laboratory at Geneva Hospital University. And also he belongs to the faculty at the Medical School of Geneva University in Switzerland. Habib will discuss now about the CT overscanning and automatic method for scan range selection using neural networks. So we are going a bit deeper into the CT imaging subjects. Please, Professor Zaidi.
Very good. Thank you very much, Mika, for the introduction, the nice words. So as preamble, I think I'll start by setting the scene and my voice to you and to John, also by saying that AI is not simply a set of fancy technical developments. I think it would have definitely an important and significant impact on our profession as medical physicists. There's not only fancy stuff for academia. Yeah, sorry for some civil engineering work going on here. So, all right, very good. So I think there are very serious initiatives at the European and international level supporting the addition of an AI component to existing medical physics curriculum and graduate programs. And the AI working with actually the European Federation of Organizations of Medical Physics, which includes obviously our CIMID moderator, published recently guideline curriculum related to AI for the education and training of medical physicists. And there are also similar actually debates taking place around the globe. For instance, this point counterpoint article published recently in Medical Physics, actually, so the apiary issue. So yeah, say something about this. And I think the wind usually comes from the States, but in this case, I think it started from Europe. But probably so almost all countries are going to follow up later on during this year, probably. So this is not really an outline, but kind of list of topics I'm going to cover here. So it goes really beyond SINFONIA, because I'm going to have just a couple of slides to introduce the technologies that we use in our facility for our research. Probably so most of the audience are not familiar with the hybrid PET-CT and PET-MRI, so just a couple of slides actually to show you those technologies. And then I'll simply focus on the different applications that we have investigated so far, so using deep learning for hybrid imaging research. It covers a number of topics, including low dose, CT, PET, and SPECT. So what you see in purple here is not going to be covered for the sake of time. Medical image segmentation is a very important and hot topic. Cross-modality image conversion, quantitative imaging. So a couple of works actually carried out in my lab, and then our focus basically on SINFONIA, also internal radiation dosimetry calculations. So John covered actually CT parts nicely, and radiomics and outcome prediction modeling is a very hot topic, but unfortunately we don't have the time to talk about this today. Well, so just to show you actually the principles of PET-CT imaging, how it works, so for those of you who never been exposed to this technology. So basically we've got a kind of an X-ray tube and CT detectors in the front here. So when then the technology starts basically by getting a scout scan, or what you call a topogram as well. So this is what you see on the left side here on the bottom. And then the technology defines basically the axial field of view. And then we start by rotating, so the X-ray tube and the X-ray detectors around the patient for a spiral CT scan, right? And then we basically push the patient to the PET detectors, which are offset by 60, 80 centimeters from the CT scanner, and then we fuse the two images, and then we present this to our physicians or radiologists for clinical diagnosis and also for reporting. So the second technology that we use in our facilities, PET-MRI. So PET-MRI is also a very promising technology. So we're lucky to have the first Philips whole body PET-MRI system installed in our facility. So this is the one that you see on the top left here. It's basically a la PET-CT technology, meaning that you've got the two subsystems separated by almost 3 meters distance, so to avoid any potential interference between the two imaging modalities. And then recently, so Siemens came up with now launched photodiode APD-based technology, which is obviously MR compatible. So the system allows simultaneous acquisition instead of sequential acquisition, which is used actually on the Philips system. And then more recently, so GE came up with their Signa, which uses silicon PMs, a more promising technology that enables time-of-flight acquisition. And then we have, there is another also manufacturer based in Shanghai in China called United Imaging, and they came up also with the new system that was FDA approved just recently, I guess in June last year. Just to show you some of the images that we gather here, so by the hybrid PET-MRI scanner, so we basically can see the typical image quality with high soft tissue contrast on MR images of the brain and the definition of the myocardium on a gated PET-MRI. So very promising technology, which is used in a number of institutions. So let me start actually discussing some of the works that were carried out in my lab, and I'll start with this ultra low dose chest CT images. So basically came up with the convolutional neural networks. I'm not going to discuss the details of the architecture and so on. And we basically use actually an X-ray CT simulator that takes into account the physics of the CT transmission data to simulate an ultra-low dose CT projection from the full dose projections in the sinogram domain by adding a statistically independent Poisson noise distribution and the Gaussian noise distribution corresponding to the characteristics that you see here in this table. So the patients were not scanned twice and just estimated through simulations the low dose CT scan from the full dose CT scan, and we used the residual convolutional neural network to generate the full dose from the ultra low dose CT images. So going directly to the results here, you can see basically the quality of the predicted CT images that were basically assessed through quantitative and qualitative metrics. So the radiologists assessed the images by sinus scores ranging from 1 to 5, reflecting kind of subjective assessment of image quality related to COVID-19 features. And so as you can see here, so the convolutional neural network actually improved significantly the quality of the predicted images. So the noise was substantially reduced. I'm not going to claim too much here, but just to really give you the impressions that we received from the radiologist. And the low dose scan was very noisy, so patchy, and it was quite difficult actually to report on those low dose CT scans. So as in many AI-based solutions, so we face the problem of outliers occurrence, and this is one nice example here that you see on the right panel that shows an example of an outlier in which the image quality was improved. So you see a reduction in the noise contents, but some relevant anatomical details were missing, and the network failed to recover the full details of the images since the glass opacity, so the what we call the GGO or COVID lesions, were converted to another type of lesions called consolidation. This was reported by the radiologist. So going to the qualitative assessment by the radiologist, so the scores went from 1 uninterpretable to 5, which is excellent image quality. And as you can see, so the full dose scan ranked first, obviously, with an overall score of 4.7, and the predictions with 4.4, so close actually to the full dose scan that was required actually for clinical diagnosis. And if we look actually to this right panel here, which basically represents the frequency of occurrence of each COVID-19 lesion type and the differences of images, we can see that GGO, for instance, that I just defined, it has the highest occurrence in all images, whereas mixed, basically all lesions have the same occurrence for all images. And changes basically in essence of the features are basically the ultra low dose group, so the GGO shifted to normal feature, whereas consolidation turned basically to GGO. So almost similar performance from the predictions using deep learning compared to the full dose data sets. So this is what was actually introduced by Mika, another work performed by one of my PhD students, Yazdan Salimi, still working, published it. So we're about to submit this work. A very busy slide here showing basically a complex flow charts adapted in this study protocol, where the aim is to assess the additional radiation dose associated with overscanning. So, and also to develop an automated scan range selection technique using deep learning to reduce the radiation dose to patients. So we created a pretty large database consisting of over 20,000 chest CT images acquired for various clinical indications, and we used a methodology that I'm going to describe in the following study to extract basically the 3D lung masks generated by neural network, and then 2D projected localizer images and masks are computed for lateral and anterior posterior directions. And then the deep learning algorithm is used to predict the lung masks and the scan ranges on 2D images representing basically the scout's views. And we did the assessment actually of the network by comparing this performance of this methodology to a human performance, basically what the technologist defines the axial field of view for scanning. So these are some of the results here. So overall, overscanning occurred in 99% and 95% of the cases in superior and inferior directions, respectively. And the extent of overscanning in the inferior direction was significantly larger. So these plots here show the additional radiation dose burden in terms of organ doses in milligray and total effective dose in millisievert to patients owing to overscanning in both directions. And more importantly, if you look to this plot here, which shows basically the performance of the deep network compared to human range selection for the outlier cases. So these outlier cases were very challenging cases that have very vague inferior boundary. Basically, so patients presenting with severe pathologies or pathological conditions like extensive pneumonia, collapsed lungs, patients with inappropriate positioning, or even overweight patients. So another study actually, carried by another PhD student, Isaac Sherry, still with this trendy topic of COVID-19 lesion segmentation. Obviously, it's required in some of the clinical indications, and if performed by the radiologist, so it's very lengthy process that we can obviously automate using deep learning technologies. And this is what we did. And by the way, so this work that was presented at the ECR, and Isaac won one of the awards of the ECR. So this is basically very quickly how it works. So we radiologists basically segmented the lungs and COVID-19 lesions. So we had a nice mixture of mild, complex, and more severe cases with a large database with studies coming from the US, China, Russia, Italy, and Iran. And then we have a convolutional neural network, which is trained actually with the manual delineations provided by the radiologist as ground truth, and then we predict for the in-scene database. So quickly to show you the comparison between the radiology segmentation for the lungs COVID-19 lesions compared to what we see on the right side, the AI segmentation. And I think you agree that's a very good agreement between the two. Probably you see it better here on the 3D illustrations. So again, so the radiology segmentation on the left and the AI network on the right side, very good agreements as well. Good. So our group has some experience also in developing computational models, and for pregnant patients, what we see basically on the left side at different gestation periods for abdominal or chest CT scans or abdo thoracic CT examinations, and these are used also for personalized or patient-specific radiation dosimetry. And there is also a set of non-human primate models that were developed recently by one of my postdocs. And obviously, you can guess that it takes a long time actually to do the segmentations manually. So the aim of this work actually is to automate the process using AI-based solutions. For the pregnant patients that I just mentioned before, and you see directly here, so without getting through the technical details, the original CT images on the left side, the manual segmentation in the middle, and the deep learning based segmentation on the right side. And I think also you agree, especially if you look to the 3D display here of coronal sagittal views of the computational models generated using manual and automated segmentation techniques, where the body is made transparent for enhanced viewing of the internal organs. And again, there is very good agreement for the two cases that you see here. You see these basically the features segmented here, and that was our target actually, to segment the features to estimate the radiation dose to the features from abdominal CT scans. And obviously, so the target is the radiation dose, not the segmentation itself, which is needed anyway for the automated radiation dose assessment. And you can see here that in the left panel, so comparison between the absorbed doses to different organs, kidney, liver, the uterus was the target actually. And on the right side, you see the relative difference of absorbed doses in target organs between the two segmentation methods, and the relative absorbed dose differences to the total body among the 32 patients involved actually in this study ranged from about -2% to 1.5%, with an average of, if I recall well, close to 0.3%, whereas the dose difference for the uterus ranged basically from -6% to plus 6%. So another work actually that was conducted by another PhD students consisted actually in implementing methodology to reduce the acquisition time or the injected activity to the patients, and we performed actually the predictions both in the image space and in the projection space, as you can see from this slide here. The prediction projection space was quite difficult because of the size of the data sets, so we did not actually exploit the time of flight capability of the scanner. And again, very quickly, for the sake of time, just to show you here some of the results. This is one of the patients injected obviously with 200 megabecquerel, scanned for 20 minutes, and then with this image mode scan to basically reduce the full dose scan to low dose scan, corresponding to 5% of the injected activity, of 5% of the total acquisition time. And this is the deep learning predictions in the image space and the predictions in the projection space. And you'll see from the quantitative assessment, if you look at the bias maps here, that the predictions in the projection space performed much better compared to predictions in the image space. And these are the scores again, so similar to what we did for the COVID study. We asked nuclear medicine physicians to perform the assessment, so giving the scores here, and you see that the predictions in the projection space, or what we call the PSS on the sonogram space, performed almost equally well compared to the full dose images. And if you look actually to the blunt Altman plots, very happy actually to see that we got kind of confirmation of the histogram analysis, in the sense that we achieved the lowest SUV bias and small SUV variance with the images predicted in the sinogram space compared to the image space predictions. And this was actually the methodology adopted also by another group that published recently in radiology. So we extended this work actually to whole body PET-CT imaging, and you see basically the same, so except that we used two different architectures, so low dose and the low dose here is shown compared to residual network and the cycle gain, and looking actually to the assessment. So compared actually to the brain, in this case for whole body PET-CT images, so we split it actually the axial field of view into two zones, so the brain and then the neck, including the torso. And good agreement was also reported, especially for the brain, and the lowest performance was achieved obviously for the torso. And more importantly, actually, so what was interesting is to look to the quantitative assessments of the malignant lesions. So we asked nuclear medicine physicians to look actually to malignant lesions through the full dose and the low dose scan, and the two residual networks that we used. And we were quite happy actually to see that the cycle gain actually enabled to delineate, so to pinpoint almost all lesions except 4, whereas the residual network missed actually a significant number of malignant lesions. And this is a nice example here where you can see one of the lesions actually lymph node that you see here, a small arrow that was seen on the full dose scan, missed on the low dose, and the image predicted by the residual network, but nicely pinpointed by the cycle gain. So problem good to skip. How long time I still have, Mika? Few minutes, couple of minutes, 3 minutes?
Yes, we have still 6 minutes, so it would be nice if you will left 5 minutes.
Yeah, let me just go quickly through those developments here. We do a lot of work also in the area of image conversion, so from MRI to CT, and the application is basically MRI guided attenuation correction and MRI only radiation treatment planning for those of you who are working in radiation oncology departments. And what you see here is the MRI of patients, the CT of patients, the predictions with the deep learning network, and the crude segmentation method actually used by the scanner manufacturer. So obviously, the deep learning network does a good job, except that, as I mentioned it earlier, so we had also some outliers. So the deep learning solutions provide actually very good results in almost 99% of the cases, but you got some outliers. So let me skip some of this work here in quantitative imaging. So we use the same type of techniques actually for attenuation correction in the image domain. But what is actually relevant for the SINFONIA project is whole body voxel-based internal dosimetry, which is actually used in the clinic. And I am aware that a number of institutions use a very simplified mathematical formalisms like the medical internal radiation dosimetry. And in some academic institutions, they use more advanced techniques, actually similar to what is used in academia or in external beam radiation dosimetry, where you would basically convolve the activity map with the dose point kernels to predict the dose distribution. And recently, so Azada, so one of my PhD students, did a very good work actually, so probably can discuss this during the debate or discussion section. And you see here that basically the deep learning networks did a very good job in terms of predicting the dose distributions compared to Monte Carlo, which uses it as a grounded truth. So with this, I think I'm just going to conclude. So I have a couple of slides basically to show you the crisis that we are facing in terms of sharing code or data sets for a development of AI-based solutions, and some caution also which needs to be, and we need to pay attention to this when ranking biomedical image analysis competitions. And I'll just stop here and thank you very much for your attention.
Thank you, Habib, for this excellent talk. And it was really, towards the end, also nice to see the internal dosimetry development in deep learning. So we have had several questions, and due to the time limitation, I will just present one very general question to both of you, and maybe one more after that. So one of the general questions actually for both of you is how fast these methods can be implemented in hospitals, in clinical practice, how far we are.
Can I start? So let me first, I rushed to finalize my talk, so I forgot to thank my AI team members, Dr. Stratakis, Mironakis, Beris, and Zanis, and others will join the team soon. Well, depending the implementation time in the hospitals, I don't think it will take time. So it has already started. I mean, it is a tsunami, and we should be, as medical physicists, should be prepared. I understand that the question is about the implementation, not about the training time, the time to train the models, right?
Clinical implementation, how fast we actually can use these in hospital.
In fact, in the US, the hospitals has already started using AI models and systems, especially for diagnosing, for example, for screening. When you have a lot of examinations to diagnose, AI is very useful, and there are several equipment and several software packages and models that have already been approved by the FDA. We know the story. I mean, the wave will come to Europe from the US. We have a delay of a few months, but it's here.
Yeah,
thank you.
Just to add my 2 cents here very quickly. I think time is not really the issue. The issue is more the clinical adoption by the radiologists and internal medicine physicians. And probably in terms of clinical implementation, we can mention a couple of white papers for CT reconstruction by Canon and GE. So these are commercial products that are used in a number of clinical institutions, meaning that we are ready. I mean, for those who are really adopting those technologies, so I think there is a scope for clinical implementation.
I agree. And one of the things we have to take care of very carefully is the clinical validation when we take these new methods into use. Unfortunately, we have run to the end of the webinar time. So we don't have time for extra questions, but please remind that these lectures are available as recorded files after 48 hours. So with this, I thank you for these excellent and inspiring talks, John and Habib. And also, I would like to thank you all for joining. I hope you enjoyed this IOMP event, and I wish you a nice springtime and stay safe. Thank you.
Thank you, Mika.
Thank you very
Tomorrow,
much, Mika.
same time, another very interesting webinar.
Good. Thank you, John.
Thank you. Thank you, Habib.
Thank you.
See
Bye.
you tomorrow.